So last time we talked about this. If I have the f of x, we're interested to find its maximum value and the point where the function attains its maximum, right? So we say that we need to do 3 steps in order to find the maximum or minimum points of the function. The first step is we need to find all critical points, right? Or sometimes we call this as extremum points. So find all critical points. So what are those critical points? Where the derivative is equal to the 0, or the derivative does not exist, right? Or on the borders of the interval. So in the next step, we need to evaluate the function at every critical point. Evaluate the function at the critical points Then in the third step, we need to compare the values, right? The largest will be maximum, the smallest will be minimum. The largest is minimum, is maximum. The smallest is minimum. Oh, did we finish this example? Was the band? Was 1 meter? Right? Okay, let's do this because we didn't do this with the second group. So let's assume I've got a band with 1 meter length. Okay? So I would like to divide this band I would like to cut this band at some point x. And I would like to create the square using this part of the rope of the band or the band and this part of this band. Okay? So what will be the length of this part? The left-hand side part?
1 minus.
It will be x, right? The length of the right-hand side part will be 1 minus x. Okay? So what I would like to do is I've got the band, right, or the rope, right? I just cut this out at some point, okay? Then I will make the square, okay? Square, okay? Like this. So, okay. So if I will make the square where the sum of all the sides will be equal to the x, what will be the length of one side? Is x divided to the 4, right? Because for the square, every side is equal to the, all the sides are equal, right? So one side is x divided to the 4. And for this part of this group, one side of the square should be equal to 1 minus x over 4, right? So the square is the rectangle where all the sides are equal, right? So for that part, for the left-hand side part, this will be x over 4, x over 4, x over 4, right? Because the sum should be equal to the x. And for the left-hand side, for the right-hand side, it will be 1 minus x over 4 for each side, right? Okay. The problem was like this. So where we need to cut this rope so that the area, the sum of the areas for both of the squares will be maximum, right? So the area for the first square is equal to the x over 4 in the square, right? Because we need to multiply the width to the height, right? So x over 4 in the square. The area for the second one is 1 minus x over 4 in the square, right? So we need to maximize this function with respect to the x, okay? So do you see that this is the function? Because by putting the different values of the x here, you can get the different values, right? So this is the function which depends on x, right? So if you put x to be equal to the 1, this will be equal to the 1 over 4 in the square, right? If you put the x to be equal to the 0, this will be again 1 over 4 in the square, right? So if you put different values of the x, you will get different values of the sum of the areas, okay? So the question is, what kind of x I need to choose in order to maximize this area, right? So last time we said, okay, so we will maximize this with respect to the x, and the first step is to find the critical points, right? So what are the borders of this x? In which interval we're considering this? Can I take x to be equal to the 2 or 3 or minus 1? No, right? So the x should be between 0 and 1, right? Because my rope is 1 meter, I can cut this at some point between 0 and 1, right? Okay, so it takes the values between 0 and 1, okay? Now, we need to find the critical points. Take the derivative of the a and equalize this to the 0 and find all the points where this derivative is equal to the 0. So what is the derivative of the x over 4 in the square? It's 2 multiplied to the x over 4 multiplied to 1 over 4, right? According to the chain rule. Plus, what is the derivative of this thing? It's 2 multiplied to the 1 minus x over 4 in the square multiplied to the derivative of the 1 minus x over 4 is minus 1 over 4, right? Yes? So derivative of 1 minus x in the 4 is equal to the derivative of 1 over 4 minus x over 4, right? Derivative of the constant will be 0, and derivative of the minus x divided to the 4 will be minus 1 over 4, right? Okay. So minus 1 over 4, and I need to equalize this to the 0 and find all the x's which satisfy this equation, right? So in all of these points, the graph will have the experiment points or the critical points, right? So the tangent line will be horizontal. Okay, so I've got this equation: 2 over 16 multiplied to the x minus. So here I don't have the square anymore. 2 over 16 x minus. So we've got the result: 2 over 16 multiplied to the x plus 2 over 16 x minus 1, right, is equal to the 0. I will multiply both parts of this equation to the 16 over 2, okay? So every term, 2 terms in the left-hand side and 1 term in the right-hand side should be multiplied to the 16 over 2, okay? So we multiply the first term to the 16 over 2, the second term to the 16 over 2, and this term to the 16 over 2. Okay? What we'll get is x plus x minus 1 is equal to the 0. Right? So from here we can find that tx is equal to 1 and x is equal to the 1 over 2. Right? But still, you need to figure out maybe this is the minimum, or maybe this is the maximum, or maybe this is neither minimum or maximum, right? So in order to check whether this is the maximum, we need to evaluate the function's value for all the points, okay? What was our function? It was x over 4 in the square plus 1 minus x over 4 in the square. Right? So instead of this x, we need to substitute 0, 1 over 2, and 1. So why we need to substitute 0 and 1? Because they are on the borders, right? Okay. So if you substitute the 0, what you get? It will be 1 over 4 in the square, right? Or 1 over 64. If we substitute 1, we get the same. 1 over 16. So if we substitute 1 over 2, what we'll get? 1 over 2, we'll get 1 over 8 in the square, right? Plus 1 over 8 in the square. Right? Yes? So 1 over 64 plus 1 over 64. One over 32. Okay, so what is bigger? 1 over 16 is bigger, right? Okay. So it means that it reaches its maximum on the borders, right? Either in 0, either in 1. Okay? So it has the minimum area at the 1 over 2. Okay? That's the conclusion. So third step. The maximum point is x is equal to the 0 or x is equal to the 1, right? And the maximum value is 1 over 16, right? So the minimum point is x is equal to the 1 over 2, and the value is 1 over 32, okay? So what we need to do is always, so we need to find all the critical points, okay? So where the derivative is equal to the 0 or the derivative does not exist, right? So do you remember we discussed when the derivative does not exist? Yes. For example, if the function has some discontinuity, right? If it is the step function, for example. Or if it has some corners, right? The derivative does not exist. Or in the infinity, for example, okay? So we need to find the points where the derivative does not exist and the derivative is equal to the 0, okay? And we need to evaluate the value, we need to find the values of the function for all of these points plus for the boundaries, okay? And in the third step, we need to compare them. Okay, so the largest will be the maximum, the smallest will be the minimum. Okay, so what we can know from the derivative, so I would like to, okay, so this is already a couple of applications of the derivatives, right? So previously we applied the derivatives in order to make the linear approximation, right? So now we apply the derivatives in order to find the maximum or minimum values of the functions, right? So today we're going to discuss more applications of the derivatives. So let's say, do you remember a couple of lectures ago we discussed the increasing and decreasing functions, right? So what do we call as the increasing function? Okay, so if you go to the right in the x line, right? Then the y also goes up. Yes? If you go in this direction, then your friend in the y direction also goes up. Okay? So what we call is decreasing function. If you go right to the right in the x direction, your friend will go down in the y direction. Right? So this is called decreasing function. Okay, so graphically it's clear, so we define this mathematically as well, right? You need to choose 2 points here, right? You choose the 2 points, x1 and x2 here. And for those 2 points, if the values of the value of in the second point is bigger than the value on this first point, then the function is increasing, right? You see, so I choose the 2 points the second point is bigger than the first one, and the value at the second point is also bigger than the value of the first one, right? So that is why this function is increasing, right? This is the mathematical definition of increasing functions. Then, so for decreasing functions, you choose the 2 points, x1 and x2. Then you evaluate its values, right, for the function. Then, which is bigger? This is f of x1. This is f of x2. F of x1 is bigger, right? If you choose the 2 points where the x2 is bigger than x1, but the value of the x2 is smaller than the x1, then the function is decreasing, right? So graphically it's clear, we define this mathematically. Now, if we're given a function, how to define the areas where the function is increasing or decreasing? So, for example, we can just draw this and figure out the points approximately, right? What if I would like to exactly know where the function is decreasing and where the function is increasing mathematically? Compare all the points? What do you mean by the slope? Oh, okay, good, good. So the idea is like this. So I need to, let's look to the slope, right? So let me make the tangent line here at this point, right? And let us make the tangent line here at this point. Okay? So do you remember what was the slope of this line? So the slope will be here positive. Okay? And the slope of this kind of line is negative, right? So we discussed this many times, right? For example, if you would like to draw the graph of y is equal to the tx plus 1, then it should look like this, okay? Like the first one. But if you would like to draw the graph of the function, for example, y is equal to the minus tx plus 1, then it should look like this. Yes? We can check it. How we can graph the tx plus 1? Tx plus 1. So we need to take the 2 points, right? So how we can find the coordinates of the 2 points on the slide? So for example, just choose 1 point for the x and find its corresponding y point, right? So if you choose x to be equal to the 0, what will be the y? 1, right? This is the first point. So if you choose x to be equal to the 1, what will be the y? 3, right? 3. So now you just need to connect them, right? Your function will be like this, right? So what is the slope of this function? It's 2, right? So when you take the derivative, it tells you that this is 2, right? The slope of this function is 2, okay? So now let's try to draw the function. Do you see that this is positive? Okay? If your function is look like this, the slope is positive or negative? Positive, right? So m is positive. Oops. If your function is like this, then m is 0. Okay? The slope is 0. Yes, m is slope. Now let's try to draw the graph of the function. Y is equal to the minus tx plus 1. Okay? So let's choose 1 point again for the x. So if x is equal to the 0, what's the y? 1. If x is equal to the 1, what's the y? Minus 1. Right? So we need to put these 2 points, 1 here and minus 1 here, right? So the graph of the function will look like this, okay? So the slope is negative here, okay? Do you see? So if it looks like this, then this is positive. If it looks like this, then this is negative, okay? So put your on your notebook, like your right hand, okay, like this, okay? Then in this case, the slope will be negative, right? If you put your left hand, then this will be positive, right? Can you do this? Put this. The right hand side, right hand is negative, right? Right hand is negative. Right hand is negative, right? Left hand is positive, okay? Right hand is negative and left hand is positive. Yes? Okay. Now, so which hand I need to put in order to correspond to this line, to this green line, I need to put the left one, right? So which means that this function is increasing, right? The slope is positive. For increasing function, the slope will be positive, okay? For decreasing function, the slope will be negative, okay? So how I can define the regions where the function is increasing and decreasing? So, yes? Yeah. Okay. If your function is always increasing, then it's clear, right? You find 1 point, for example, right? And it's always positive. So if it is increasing and decreasing, how to find the regions where it is increasing and where it is decreasing? Huh? Tell me the idea, the concept. No, like, I'm not asking you what to do step by step. Tell me the idea. For example, like this. So your function is increasing until some point, then start to decrease, right? So tell me, in which regions it is increasing, in which regions it is decreasing? Okay, so I need to find the slope of the tangent lines, right, for all the points, right? Okay, then you will go starting from here. If it is positive, 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 right? Left hand, left hand. Then here it becomes like a 0, right? And after 0 it becomes negative, right? Basically, we need to find the intervals, okay? So we need to find it. Let's do this like this. So let's do an example. I hope you did this thing in a school, right? Yeah. So when you find the regions when your function is positive and negative, right? So the same thing. So you find the derivative of the function, and you find the regions where the derivative is positive and negative, right? So when the derivative is positive, it means that your function is increasing. When the derivative is negative, then your function is decreasing, okay? So let's do this. So let's say I've got a function is 3x4 minus 4x cubed minus 12x squared plus 5. All right? So we need to find where this function is decreasing and where this function is increasing. Okay? So in order to do this, so we decided, okay, so we need to find the regions where the derivative is positive always, and the regions where the derivative is negative for all points in that interval, in that region, right? So let us find first of all the derivative of the function. Derivative of the function will be equal to the 12x cubed minus 12x squared, right? Minus 24x plus 0, right? So in order to find where this function is positive and where this function is negative, this function, right? I need to find its roots, right? Then I need to put the intervals, right? So do you remember how to find the roots? Yeah, what does it mean, the roots? Finding the roots? Find the points where this function becomes 0. The value of the function is equal to 0. Find me all the axes where the f of f prime of x becomes 0, right? So let me take out the 12x out of the brackets, right? 12x. Then what is left is x squared minus x minus 2. Okay? So we can write this down as 12x, x minus 2, x plus 1. Okay? So in which three axes this function becomes 0? When x is equal to the 0, when x is equal to the 2, and when x is equal to the minus 1. Okay? So in order to find the regions where this function is positive and negative, we need to put the 3 points on the interval of the x, right? So -0, -1, and 2, right? Then we need to split this, the whole interval of the x. There's the 4 different parts, right? The first part, the second part, the third part, and the fourth part, right? If we choose any point more than 2, this function becomes positive, right? So you can check it. For example, if you choose the 3, and if you put it here, right? This is positive, this is positive, this is positive, right? So it means that the function is positive. So here, for all the points more than 2, the function is positive. For all the values between 0 and 2, the function is negative, right? For example, we can choose the 1, right? From here. So 1 minus 2 becomes negative. This is positive, this is positive. So that is why the multiplication is negative, right? So minus, then plus, then minus, right? So the conclusion is like this. So for all the points where the x is more than 2, the derivative of the function is positive. It means that function is increasing in this region from 2 until infinity, right? So for all the points between 0 and 2, the derivative of the function is negative, right? The right-hand side part. The right-hand side, right-hand, right? So derivative is negative. It means that your function is decreasing here, right? For all the points here, your function is increasing. And for all the points here, your function is decreasing, okay? So obviously, it is really difficult to draw this graph, but we can try to... okay, so let's try to make this graph. So I need to draw -1, 0, 2, right? Okay. So let's start from the beginning. So it decreases until -1, right? Then it starts increasing. What is the value of the function at the -1, by the way? What was the function? No, not the derivative. The function itself. The function was 3x² minus 4x cubed minus 12x squared plus 5, right? If you substitute -1 to here, what you get? 3 plus 4 minus 12 plus 5, right? Which is 0, okay? The derivative is also 0, the function is also 0. Okay, so if the function is decreasing until here, until the -1, then start to increase, what will be the shape of this function? It goes down, then goes up, right? Do you understand this? Goes down, then it goes up, right? Now let us evaluate the value of the function at the point 0. Okay? If you put the 0, what you get? 5, right? So at the point 0, your function should be here, 5, right? Now let us look to there, right? So it tells me that before 0, it was increasing. After the 0, it is decreasing, right? So it should go up until the 5, then go down, right? Do you understand this? What is going on? So it goes up. Then down. Okay, now let us calculate this at the f of x is equal to the 2. So this is 3 multiplied to the 16 minus 4 multiplied to the 8 minus 12 multiplied to the 4 plus 5. So this is equal to, let's do this. 48 minus 32 minus 48 plus 5. Did I calculate correctly? Did you calculate this as well? So you need to check me. So 48 minus 32. 42, what? 48 will cancel each other. Okay. This is correct, right? Okay. So here, the third point is here, right? So when x is equal to the t, the y is equal to the minus 27, right? So how the function should look like? So until this t, the function will decrease, right? At the t, it will start to increase, right? So the function should look like this. Right? Yes? You understand this? So we found out the values of the function at this critical points where the derivative is equal to the 0, right? Then, just using the signs, whether the function is increasing or decreasing, we just drew this function, right? So this is what you need to do in exam probably, okay?
We should draw coordinates too, or just show this.
You need to draw the coordinates as well, right? Okay, now, do you remember last time we discussed two things, right? We say that there exists the absolute max mean and local max mean. So what is the difference between the absolute max mean and the local max mean?
Absolute is global.
Yes, the global and absolute is the same. Absolute means global. So what is the difference between the absolute maximum minimum and the local maximum minimum?
Global is where the maximum or minimum in the whole function.
No. So, okay. So you tell me, the absolute one is the greatest, right? But why we call then this thing as the maximum as well? Maximum of what? Okay, here in this example, what is the absolute minimum and what is the absolute, what is the absolute minimum and local minimum? Minus 27 is absolute minimum. This one is local minimum, right? So what is the local minimum? Is when your function is going down and up, okay? But it is not the smallest, okay? So if your function is going down and up, but if it is not the smallest, then this is the local minimum, okay? If your function is going up and down, but it is not the largest, it will be the local maximum, okay? For example, this one is local maximum because your function will increase there, okay? It will be bigger than this value, okay? And here as well. So this is the local maximum because it goes up and down, okay? Now, you need to tell me the tool. Or last time we discussed this, right, already. So we said, okay, so intuitively this is true, right? So I need to figure out the points where the derivative is equal to the 0, right? Then the largest will be the absolute maximum. The smallest will be the absolute minimum, right? And we said, okay, so we asked the question, so how to figure out whether the points, the other points, are the local minimum or local maximum. How we can figure this out? We need to look to the signs of the derivative before this point and after this point, right? If before this point it was minus, then after this is plus, it means that this is local minimum, right? If it was minus before this sign, it was decreasing, then after this it's increasing, it means that this is local minimum, right? If for the point the derivative is positive before the point, and negative after the point, it means that this is local maximum, right? So this is how we can figure out whether these points are local minimum or local maximum. So let's try to do this. An example. So we're given a function g of x is equal to the x plus t sine of x in the interval between 0 and t pi. So we need to find the local maximum and local minimum values. Okay? I mean, obviously, this function has no the global maximum and global minimum, right? Because if you would increase the x until the infinity, then x would go until the infinity. So the f of x, g of x also goes to the infinity, right? So if you put the infinitely large number here instead of x, then g of x becomes also infinity, right? So it goes until infinity, and it goes until infinity in the negative direction as well, right? So we can find the local maximum and local minimum. What we call is the local maximum if your function is going up and down, right? Local minimum is when your function is going down and up, right? So we need to find the local minimum and local maximum. So in order to do this, again, we need to find the derivative. Then we need to find the signs of the derivative of this function, right? So let's find the derivative of this function. What will be the derivative? 1 plus 2 cosine of x, right? So in which values of the x between 0 and 2 pi, this becomes 0. So I need to equalize this to the 0, right? Then we need to figure out the axis. So basically, the cosine of the x should be equal to minus 1 over 2. So at which points of the x this function is, the derivative of this function is equal to the 0. Two pi over 3 and 4 pi over 3. Okay? So the 2 pi over 3 and 4 pi over 3, the cosine of x becomes negative minus 1 over 2. Okay? So do you remember what was the x? Is it the x line or the y line? The cosine. X. So it means that this is positive in the first quarter and in the fourth quarter, right? So 2 pi over 3 is in the third quarter, right? Okay, so the negative, the cosine's value will be negative, okay? So now we can derive this to the in this regions. So I need to put the 2 pi here and the 0 as well. 3 different regions. Okay? So between 4 pi over 3 until 2 pi, this is positive. Between 2 pi over 3 and 4 pi over 3, this is negative. And between 0 and 2 pi over 3, this is positive again. Okay? So you need to tell me at which point this function, g of x, attains its local minimum, and at which point it attains its local maximum. I'm not asking the absolute one, right? I'm asking the local one. So what is the local minimum? It should go up, it should go down, then up, right? Which point here out of this 4 is the point where the function attains its local minimum? Local minimum. It's 4 pi over 3, right? Because the function goes down until 4 pi over 3, then goes up, right? At which point the function attains its maximum? At 2 pi over 3, right? Because before this point it is increasing, then after this point it's decreasing, right? It's a local maximum. So local maximum is at x is equal to the 2 pi over 3, right? And the local minimum is at x is equal to the 4 pi over 3. Good? Okay. So there are two more things on the functions. So we previously defined whether the function is increasing or decreasing, but it is for us also important to know whether the function is concave upwards or downwards, concavity. Hmm? Hmm? Oh, what do you mean? No, concavity? No, so I will show it to you. So we call the function as concave upwards. if it looks like this, okay, we call this as a concave up. And we call this function is concave down if it looks like this, okay? So if it looks like this, if the parabola looks like this, right, this is concave up. If it looks like this, then this is concave down. Concave up, you put your croissant like this, right? Concave down is when you wash this and put this there, right? Concave down. This is concave up when you're cooking, concave down when you're not cooking. Okay? Now, what kind of mathematical definition we can figure out using the tangent lines, for example, for the concavity?
When the slope of the tangent line is positive, the function is
Like going down.
When the slope of the tangent line is positive, then this is concave up. But what about the straight line? For the straight line, this might be, the tangent line is always constant, right? Okay. So there is another definition, maybe which is not so straightforward. So the definition of the concave upward is that all the tangent lines are lying below the graph of the line. And for the concave downward, all the tangent lines are lying above the graph of the line. Okay? So this is how we need to define this. Let's define this definition. So the function is called is concave upward in some interval if all tangent lines lie below the graph of the function. And concave downward if all tangent lines lie above the graph. Of the function. So there is a reason why we're defining this. So previously, do you remember we said, okay, so for us it is important to know whether this is the local maximum and local minimum, right? So if I found the extremum point where the derivative is equal to the 0, and if the function is concave up at that point, then function attains its minimum, right? Yes? Do you understand this? So previously what we did, so we figure out the points where the derivative is equal to the 0, right? Then we found out the intervals where the derivative is positive and negative, right? It tells us whether the function is increasing or decreasing in those intervals. But if it would be the polynomial, we could find the derivative, then we could figure out the roots of that polynomial, right? So we needed the roots in order to define the areas where this function is positive and negative, right? But what if the derivative is super difficult function where finding the roots will be really infeasible? In this case, we need to figure out another method to figure out whether this function attains its local minimum or maximum at this point. Do you understand what's going on? No? You don't? Okay. So previously here, I found the derivative of the function, right? Then we said, okay, so if I would like to know whether the derivative of this function is positive or negative, we need to find the roots of this function, right? Basically zeros of the function, or basically points where the function is equal to the 0, right? Then we found out the regions where the derivative of this function is positive and negative, right? What if you cannot find the roots of the derivative of the function? Let's say I will give you like a really complicated function where you cannot find the roots of the derivative. You can find the derivative, but you cannot find the roots of the derivative. What to do in this case? You cannot find the roots. It means that you cannot find the intervals where the derivative is positive or negative exactly. Right? So for such a cases, we need to use the concavity. Okay? So the idea is, behind of this is to figure out whether the point is local minimum or local maximum without finding the increasing and decreasing regions. Okay? Do you understand this? So previously, we said, okay, so this point is local minimum because before this, the function was decreasing, and after this, the function is increasing. Right? Now, I would like to know whether this t is local minimum because of not the increasing or decreasing, because whether this is concave upward or downward. Okay? So, could you please tell me whether the function is concave upward or downward at the t? Is it concave upward or downward at the t? Concave up, right? At the t. Because it's going up, down first, right? Before the t, then up. Concave up. So at the 0, it is concave down, right? Because before 0, it is increasing, right? It's increasing for you, right? Then it's decreasing, right? Concave down. So what we need to do, ideally, is like this. So we need to find the points where the derivative is equal to the 0. Then we need to say, okay, so we need to somehow figure out whether the function is concave up or down at those points, right? So at those points where the function is concave up, they are local minimums, okay? Those points where the function is concave down, the function attains its local maximum there, okay? Do you understand why we need this concavity? One more time. Should I explain one more time? Yes? Without knowing, yes, without knowing the roots, without knowing the 2, 0, and so on. Without knowing the roots. Okay? Basically, you need to find the roots anyway. Yeah.
Don't give us overcomplicated.
You should hope for this. The idea was the concavity is like this. So, so you find the points where the function's derivative is equal to the 0. Okay? For example, at the point 3, the function's derivative is equal to the 0. You compare the values at the point 3 and in the borders. Then this value there is not the absolute maximum, for example. Okay? And now, or not the absolute minimum neither. You would like to know whether at this point the function attains its local minimum or local maximum. Okay? The first way, what you need to do is you need to figure out whether the function was decreasing before this and increasing after this, right? Or you need to know whether the function was increasing before this and decreasing after this, right? Or the second way is you should know whether the function is concave upward at that point or concave downward at that point, okay? If the function is concave upward at that point, then it means that this function attains the local minimum at this point, right? So if the function is concave down, then the function attains its local maximum there. Okay? Now you need to tell me another thing. So how to know whether the function is concave up and down? So let's say you're given a function, right? So previously we say, so I can figure out using the tangent line. Okay, so I would say using the tangent lines.
Oh, yeah.
Okay, using the tangent lines. Do you know why? So let me draw. So this function is concave up in this region, right? So let me draw a couple of tangent lines. Okay, the one tangent line, the second tangent line, and the third tangent line. Okay? Could you please tell me how the values of the slopes are changing? Are they changing? They are changing. They are increasing, right? It means that the slope of the tangent line is increasing function if the function is concave up, right? Again, if the function is concave up, then the slope of the tangent line is increasing, right? So how I can know using the derivatives whether the slope of the tangent line is increasing? By finding its derivative and showing that this is positive. Yes? Okay. So if function is concave up, then the slopes are increasing. Right? What was the slopes? It was f prime of x. Right? F prime of x, now it's a function, and this function is increasing. Right? If your function is concave up. So how do I know whether this is increasing? By taking the derivative of this and checking whether this is positive or negative, right? Okay, so this is positive, this is increasing, the slope is increasing. If ft prime of x is positive, right? So if f prime of x is positive, it means that your function f of x is increasing. If ft prime of x is positive, it means that your f prime of x is increasing. Right? Yes. So what happens if your function is concave down? Like the slope decreases, right? Because when the slope is horizontal, it is equal to the 0, right? So when the slope is vertical, the slope is the infinity, the maximum. Okay? So it is 0, then it becomes more until this point, until vertical point. Then after the vertical point, it goes down. This is 0. Okay? So in this case, it is decreasing. Right? So it means that if your function is concave down, then the slopes are decreasing. The slopes are f prime of x, right? So f prime of x is decreasing means f prime of x is decreasing means that ft prime of x is negative, right? Concave down. I mean, everything is a simple idea, right? What's the derivatives? Again, so could you look to this example now? So let's say here, at this point, you figure out that derivative is equal to the 0. Okay? So you've got a f of x. You've got a f of x. Derivative of this function is equal to the 0 here. Okay? So f prime of x or f prime of c is equal to the 0. Right? At the c. And now you would like to know whether this is the local maximum or local minimum. Right? You take the second derivative of this function at this point. Okay? You take the second derivative of this function at this point. And this is now is what? Negative. Negative, right? Negative. Why it is negative? Because this is concave down, right? If this is concave down, then the second derivative is negative. If it is concave up, then second derivative is positive. Okay? But if it is concave down, it means that it is maximum. Okay? So this is for the local maximum. You see? So the first derivative is equal to the 0. The second is negative. It means that this is maximum. Okay? Some system, right? I mean, this is clear from the image, right? So you see that this is maximum. It is positive. It means that you're cooking, right? It means that this is minimum, right? Okay, so if the graph of the function looks like this, at some point c, the first derivative of the function is equal to the 0, and the second derivative of the function is positive because your function is concave up, right? If the second derivative is positive, it means that your function here attains its local minimum. Okay? So everything we're doing is to figuring out the local minimums and local maximums without drawing the functions. Right? Okay, let's discuss the concavity for this function. Or, example. Let's say f of x is equal to the x in the power of 4 minus 4x cubed. Okay? Let's discuss where this function is decreasing and increasing, and where this function is concave up and concave down. Okay? So f of x. So I need to take the first derivative in order to know the regions where the function is increasing and decreasing, right? So this is equal to 4x cubed minus 12x squared, right? So I can take out the 4x squared out of the brackets, and what is left inside is x minus 3, right? So I can know where the function is decreasing and where it is increasing. So 0 and 3. So for all the points more than 3, this function is positive, plus, right? For all the values between 0 and 3, for example, if you choose the 2, right, then this is minus. And for all the points which are less than 0, this is minus again. Right? Because there is a square here. Right? For example, choose minus 1, right? If you put the minus 1 here, this will be positive, and this term is negative, right? So this is plus, minus, minus. Right? So I've got this point where the function is not concave down or concave up. Right? What does it mean? So let's find the second derivative. So we will find the second derivative of this function. What is the second derivative? Is 12x squared minus 24x, right? We can take out 12x out of the brackets, and what is left is x minus 2, right? Yes? So I've got 0 and 2. For all the points more than 2, this is concave up, right? For all the points between 0 and 2, this is concave down. And for all the points between minus infinity and 0, this is up again. Okay? So can we try to draw this function? Yeah? Does it look like strange for you? So now we need to combine these two things, right? We need to combine we need to combine the increasing and decreasing regions, and we need to combine the concavity, right? So I know that from minus infinity until 3, this function is decreasing, right? Okay. But at the point where at the point 0, it should what? It is 0, right? But like it should have derivative to be equal to the 0. The tangent line should be horizontal, right? It should decrease, but it should not be like a decrease like this, right? There should be something here, right? So what do you think? What is going on there? No, this function is continuous. Do you remember last lecture we discussed the graph of the x cubed, right? And we've got a point where derivative is equal to the 0, but this is neither minimum, neither maximum, right? It still will increase, right? Yes, do you remember this? X cubed. It looks like, for you, it looks like this, right? It is increasing function at the point x is equal to the 0. It has the horizontal tangent line, right? But before this, it was increasing, and after this, it was increasing, right? Yes. So it will be like this. So before the x reaches the 0, this is decreasing, but concave up, right? What does it mean, concave up? It should look like this, right? So it will be like this. Let us do this. It will be like this, right? So after the 0 until the 2, it is decreasing again, right? But this is concave up. It should be like this, right? So it will be until 2. It should be like this, right? You see? So this is concave up until the 0, and until the 2, it's concave down, right? Then after the 2, it's again concave up. Huh? It will be again, so, but still decreasing, right? Until the 3. Until the 3, it will be like this, right? And after the 3, it will be like this.
Can we draw both of them separately?
Yes.
Coordinates separately. One country.
So it will be difficult. It will be difficult to figure out what is the shape of the function. Yes? So this is like the true shape of the function. We can check it using the computer graphics tools. Like, do you understand what's going on? One more time. So before the 0, the function is decreasing and it's concave up, right? Because here is plus, right? It means that it should look like this. After the 0, it's still decreasing, but it's concave down now, right? It should be like this until the 2. And after the 2, it's concave up, right? But it's decreasing until the 3, right? You see, so this is concave up, right? So maybe starting from here, right? So concave up. And after this, it's still concave up, right? You see? So here, right? Concave up. Okay, so we need the first derivatives and the second derivatives in order to sketch the graphs. This is an exercise.
We'll be asking for finding shape of the
Yes.
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 We don't ask this, we can draw it separately.
Yes. Okay, now the last thing is called the points where. Okay, could you please? So these 2 points are really spatial points. These 2 points are spatial points. Because, not exactly this one, probably this one here, the 2, right? So these points are special. So the points x is equal to the 0 and x is equal to the 2 are spatial. Okay? They are spatial because at those 2 points, they are changing their concavity. See, they are neither maximum, neither minimum, but they are changing their concavity. Okay? So here, at the 0, it's changing the concavity from like a concave up to the concave down. And at this point, it's changing its concavity from down to the up. Okay? So these points are called the inflection points. So you'll be asked in exam also to find the inflection points as well. So the points P of the y is equal to the f of x are called as inflection points if f is continuous and it changes its concavity there. Inflection points. So mathematically it means that this is the point where the second derivative is equal to the 0, right? And the second derivative is negative and positive, or positive and negative. You know what I mean? Yes? So here. Plus, minus, plus, right? So these 2 points are the inflection points because the second derivative is equal to the 0 in these 2 points, right? And at this point, the function, the curve of the function changes its concavity, right? Before this, it was concave up, then down after this. And before this, it was concave down and up after this, right? So if the second derivative is equal to the 0, and if it is like the function's value before it was plus and after it becomes minus, it means that this is the inflection points. Okay? They are important points. So we will use them later. Good? So using the second derivative, so you see, so just using the derivatives, we can know a lot of things about the functions, right? So we can know the regions where the function is increasing, decreasing, when the function is concave up and down, when the function has the maximum and minimum, the local maximum, the local minimum, right? Many things. So in the next lectures, we're going to discuss the more applications of the derivatives.